Thank you for the introduction, and thanks to the organizers for putting the conference together. I'm going to talk about group actions on exotic spheres. This is 3 separate projects with Boris Botvinnik, Oliver Wang, and Tilman Bauer. The last 2 are in progress. The work with Botvinnik is done, hopefully. So I'll start with talking about exotic spheres, and then I'll talk about group actions on them, and then we'll stop. Okay, so an exotic n-sphere is a smooth n-dimensional manifold which is homeomorphic but not diffeomorphic to the n-sphere with its standard smooth structure, which I'll always denote by Sn. All right, you know what an exotic sphere is. Good. So the beginning of the study of exotic spheres is Milner's result from 1956, which says that exotic 7 spheres exist. Since then, there's been a lot of work on classifying exotic spheres, and maybe some of this is summarized in a conjecture of Wang and Xu, I think from 2017, which says that the only dimensions n greater than or equal to 5. We haven't had any talks about 4 manifolds, and we won't. I don't think. Okay. So the only dimensions n greater than or equal to 5, in which the n-sphere admits a unique smooth structure. So this is up to diffeomorphism. Admits a unique smooth structure are the following. So there's dimension 5 and 6. This was known a long time ago. 12, 56, and 61. Okay. So if the conjecture is true, there's a lot of exotic spheres, and there's a lot of evidence that even if you don't know the conjecture, tells you there are a lot of exotic spheres. So the conjecture is true for n odd, and this is many, many people's work. So let me mention Wang and Xu. There's also Hill, Hopkins, Ravenel. Browder, Perver, Milner, and then there's probably people who are much more well-versed in the history here, so you can fill it in. Okay, so if n is odd, the conjecture is true. If n is less than 140, the conjecture is true. This is pretty recent work of Behrens, Hill, Hopkins, Mahold, which also uses work of Isaacson. And it's also true for over half of all even n, and this was recent work of Behrens, Mahold, and me, which I'm not going to talk about today much. Okay, so the upshot of this discussion is that there are a lot of exotic spheres, and the question is, in what ways are exotic spheres like standard spheres. And there's many ways you could ask this question. You could mean symmetry, or you could mean curvature. Curvature, I think, is really interesting and like a super hard problem. So we're not going to talk about it. Instead, we'll just focus on symmetry today. So the main question for the talk is how symmetric are exotic spheres? Okay. I guess I should have checked like one board ago, but are things big enough and am I loud enough? Okay. Am I too loud? Okay. I took my glasses off, so I don't know how far away the room is. Okay, so you can quantify how many exotic spheres there are, which is just a number. It's a little harder to quantify how symmetric an exotic sphere is. But there are various ways of doing this, and we're going to just focus on one sort of coarse measure of symmetry called the degree of symmetry. So the degree of symmetry of a smooth, compact, connected manifold M is the following number. So I'll denote it by n of M, and it's the maximal dimension of a compact Lie group which acts smoothly and effectively on your manifold. So let me write that. It's the maximum taken over G, a compact Lie group, of the dimension of G, where G acts on M, smooth and effective. And maybe as a reminder, what does effectively mean? So this means that if Gm equals M for all M and M, then G was the trivial element in G. So another way to say this is the only element of G which acts trivially is the identity element. Okay. Any questions so far? Cool. Okay, let me give one example where you can actually compute the degree of symmetry. So the degree of symmetry of the standard n sphere is the dimension of SO n plus 1, where I think of the n sphere as sitting inside of Rn plus 1 and SO n plus 1 acts by rotations. This dimension is n times n plus 1 over 2, or approximately n squared over 2. So as a remark, knowing something about symmetry actually sometimes tells you something about the manifold. So a remark, if M is a simply connected smooth n manifold, then if the degree of symmetry of M is that number, n times n plus 1 over 2, then M is actually diffeomorphic to the standard n sphere. So maybe I'll put a little C infinity to say diffeomorphic. Okay, great. I guess I can write a little lower on this side. Yep.
How would you show something like this?
Well, when I read papers on this stuff, they say it's an exercise that you can read in like a standard differential geometry textbook. I don't know off the top of my head. if there's like a fast way to say it. Sorry. Other questions?
So what about the bonus 7 spheres? Is this number known for those?
Yes. So we're getting to exactly your question, which is the following theorem. So thanks for asking. Well, we're slowly getting there. So work of the Shangs, Shang and Shang, one that you know from trace methods and one that you don't know from trace methods. Yes. Yeah. So presumably one you know from trace methods. But. Okay. So Shang and Shang proved in 1967 that if sigma n is an exotic n-sphere, and n is at least 40, then the degree of symmetry of sigma n is at most n squared plus 7 over 8, which is approximately n squared over 8. And so above dimension 40, exotic spheres are at most 1/4 as symmetric as standard spheres. Okay? Fine. Well, this question of, or this observation of Shang and Shang led to the following question. So this first appeared, I think, in some conference proceedings on a conference on transformation groups from '67, asked by Shang and Shang. And it was asked again in '85 by Reinhard Schultz. And not much progress was made in between then, so it's still a good question. Okay, that's a big number, but you can ask something simpler. Is the degree of symmetry of every exotic sphere positive? Say for every exotic sphere sigma. Which I think is a really natural question. When you think about a sphere, you think about two things. You think about how it's round, and you think about how the Earth is a sphere and it's like rotating around an axis. And like, if you lived on an exotic sphere, this is asking, could it like, would you have day and night, basically? I guess a Zeeman 2 action is day and night. It's would you have time? So a lot of work has gone into studying this question. And to tell you what is known, I have to tell you about different kinds of exotic spheres. So this is mostly from the work of Kerver and Milner from 1963. So as in the conjecture above, I've tried not to use n for anything else but dimension. So n is always going to be at least 5. And there's several groups that I want to study. So theta n is the group of oriented diffeomorphism classes of topological n-spheres. So theta n, or the cardinality of theta n, is telling you something about how many smooth structures the n-sphere admits, maybe up to a factor of 2, plus or minus 1. Sitting inside of theta n is a subgroup called theta nbp, and this is the subgroup of n-spheres which bound parallelizable manifolds. So the reason this is a kind of nice subgroup to study, well, one, it's a subgroup. I should say the group operation is connect sum here, where you're kind of careful about things. The reason this is a nice subgroup is because the standard n-sphere bounds a disk which is parallelizable. So this contains the identity element. And it's a sort of natural geometric property to ask for. Okay, so these are the sort of manifoldy type of things that we care about. We also care about less manifoldy things like the nth stable stem. Higher. So this is the nth stable stem, or the nth stable homotopy group of the sphere, which sometimes we write like this, sometimes we write it like that. Sorry. Okay, so it's just some homotopy groups of spheres. All right, and then finally, to state this sort of classification of exotic spheres in terms of stable homotopy, we also need to recall the stable J homomorphism. So this is a group homomorphism from the nth homotopy group of the infinite orthogonal group into the nth stable stem, which is basically gotten by one-point compactification and some sort of stabilization. For the purpose of the talk, it doesn't actually matter how it's defined or what it is. Okay. So I have these 4 things on the board. It'd be bad to put them there if they weren't related. So Curvaire and Milner in '63 proved the following. So first, theta 4k, a group of 4k dimensional topological 4k spheres up to these adjectives, is isomorphic to the co-kernel of J in dimension 4k. So if our dimension is divisible by 4, we have this nice description of all exotic spheres in terms of something from stable homotopy theory. And there are also exact sequences for the other congruence classes of dimensions. So we have 0 mapping to theta 2n plus 1 BP, includes into theta 2n plus 1, and the co-kernel of this map is the co-kernel of J in dimension 2k plus 1.
You meant to keep inserting n for the dimension, so you meant to have k's in the first 2 terms.
Oh, yeah. Thank you. All right, and then one other exact sequence, 0 to theta 4k plus 2, co-kernel of J 4k plus 2, some no longer mysterious map called the Curvaire invariant to Z mod 2, and then theta 4k plus 1 BP 0. Okay, I should say I'm lifting this review from Behrens, Hill, Hopkins, Mahowald. So it's in the introduction to their paper, I think. Okay, so we have these exact sequences expressing theta n, the thing that we care about, in terms of theta n BP and this co-kernel of J, and the Curvaire invariant. Let's totally reduce to studying the co-kernel of J. So Curvaire, Milner, plus many others, worked out the order of these theta n BPs and also what this curvaire invariant is. So I'm thinking like Hill, Hopkins, Ravenel, Browder, Lin, Wang, and Xu recently. So theta n BP, we can say explicitly what this is. It's a trivial group if n is even, or n is 5, 13, 29, 61, or 125. Theta NBP is Z mod 2. If n is 4k plus 1, and it's not in the set that I just wrote down. And otherwise, it's some cyclic group, which I'll write as Z mod T sub k. If n is 4k minus 1, sort of ran out of space here, so let me just put the little remark. This tk is an explicit number that you can compute in terms of numerators of Bernoulli numbers. For the sake of this discussion today, tk is always greater than 1. In fact, it's like a bajillion if k is like not that big. Okay, so we have a lot of exotic spheres, and classifying them basically reduces to computing the co-kernel of J, which is, well, we know the image of J from atoms in the 60s, so it's really computing the stable stems. So we'll never do this, but we can try. Okay, so now I can tell you in terms of this language, what's known, or what I think is known about group actions on exotic spheres, or degree of symmetry. So there's first some follow-up work of the Shangs. And it's really like 2 joint papers between them and 1 by Wu Yishang. So I wasn't sure how to denote this. So I guess it's also not clear. This one's Wu, okay. From 67 and 69. So if I restrict attention to exotic spheres which bound parallelizable manifolds, we can actually say pretty precisely what the degree of symmetry is. So first, if sigma bounds a parallelizable manifold and sigma is n-dimensional, then with the same sort of restriction on n as above, then for n greater than or equal to 40, the degree of symmetry of, let's say, sigma n is equal to n squared plus 7 over 8. So this is true for the curvaire spheres, which you asked about. In the other congruence classes, so 1 mod 4, I need a little fudge factor. So this is with epsilon between -1 and 1. Okay. All right, so if we bound a parallelizable manifold, we're actually pretty symmetric, like a quarter as symmetric as the standard sphere, and like that's as symmetric as we can be. On the other hand, if sigma does not bound a parallelizable manifold, and n is at least 300, then the degree of symmetry of sigma is bounded above by, okay, I looked it up this morning, n plus 1 squared over 16 plus 5. Okay, so I know everyone's a mathematician, so I don't have to do this, but these things are at most a quarter as symmetric as these things, which were at most a quarter as symmetric as I'm sorry, these are at most half as symmetric. It's good that you're all mathematicians, so you could understand what I meant. Okay, and let me remark that there's some work that I forgot about until this morning. So Schultz, did I put a date? Nope. Okay. For a certain family of exotic spheres, these are in dimensions, I think I want 2p squared minus 2p minus 2 or something. And I'm going to call this n. You can actually get an even better bound. So the degree of symmetry is at most 30 n over 7 plus some constant that I don't remember. Okay, so for certain exotic spheres, which some of you can tell are related to chromatic homotopy theory, you actually get a linear bound on the degree of symmetry.
P's a prime.
P's a prime. Yeah. P is a big prime, like 5.
In view of these two young theorems, I mean, how can you have epsilon equal plus 1? I mean, in view of the other theorem?
I guess if it's
I mean, you have, the other one is for all.
right. That's a good point. Maybe you can. Yeah, I think that's good. Thank you. I was trying to convert an inequality from that paper into this earlier. So. Okay, thanks. Other questions? Cool. All right, so what you'll notice here is that for exotic spheres which bound parallelizable manifolds, this question is basically answered of the degree of symmetry. For ones which don't bound parallelizable manifolds, we only have upper bounds in general, which is kind of not the most satisfying thing because it still doesn't tell you if you can smoothly rotate these things. So, I forgot where I am. I guess I can get rid of the question. No, I can get rid of this. It works out. Okay, good. So we're going to restrict attention to exotic spheres which don't bound parallelizable manifolds. I'm not going to put up this terminology because I think it only appears in the work of Reinhard Schultz and me. But from this perspective, the exotic spheres which come from the co-kernel of J are very exotic. So I might sometimes refer to these as very exotic spheres, those which don't bound parallelizable manifolds. But I'll try not to do it because maybe it'll make the ones which bound parallelizable manifolds feel not very exotic. Okay, so what's going to be our approach? These exotic spheres which don't bound parallelizable manifolds are coming from the co-kernel of J, which is something in stable homotopy theory. So we're going to try to detect symmetries using stable homotopy theory. And here's a sort of prototypical theorem. This is C.N. Lee in 67. Suppose P is a prime. P equals prime is prime to the order of some exotic sphere sigma in theta n. So I just mean like if sigma is only 2 torsion, take P to be not 2. Then sigma admits a free Z mod P action. I guess I should say smooth, but for the rest of the talk, and I think since the beginning of the talk, all actions are going to be smooth. Okay, so, and it's like a 1-page paper. You can just read the construction, and okay, you can do this.
How many density are the three?
Probably. Thanks.
Or you could erase and, oh, no, and the dimension of the sphere.
Oh.
Or you could erase n, or sorry, or you could erase 3 and so on.
I see. I'm just going to make n odd. Thanks. Thank you. Oliver was explaining the paper to me like a week ago. Okay. So this is a sort of prototypical example of a theorem that I want to be able to prove. And just as an example of like what this looks like in practice, you can look up, or just compute if you know the stable stems in a range, the prime factors of the order of theta 20. So if we stare at that theorem up there, theta 20 is the co-kernel of J in dimension 20. And so this is really just something you can compute in terms of stable homotopy theory. The prime factors are 2 and 3. So the exotic sphere detected by kappa bar in the co-kernel of J in dimension 20 admits a free, now I see why I wanted odd. And I didn't look this up ahead of time. I think this is about right. So there's certainly a 2 there. Let's say eta kappa bar in co-kernel of J21 admits a free, let's say Z mod 5 action. Okay, I'm adjusting on the fly, so I don't actually know what the odd primary stable stems look like off the top of my head. Does anyone know if pi 21 stable is like 0 odd primary? Okay, exercise. Okay. But in principle, this is sort of how you apply it. You just compute everything and then you say the geometric application. So the general strategy will be to try to detect symmetries using stable homotopy theory. And I guess really what I mean is using stable homotopy theory computations. At some point, you also have to do some sort of geometric topology to say that these computations actually do something, but I don't really want to talk about the geometric topology. Okay. So from now on, I'm going to work in the 2 complete setting. For the most part. I should keep that towel somewhere. Maybe while I erase, are there any other questions at this point?
According to Ravenel's tables, pi 21 is 0 at the prime 5.
I know if I choose a prime big enough, then I'm good. Thank you. The problem with remembering Ravenel's tables at the prime 5 is that there's like too many numbers at the prime 5. Okay. So what is this theorem really saying? It's saying that if some sort of relation holds in the stable stems, then you could say something about symmetry of some corresponding exotic sphere. So I'm going to tell you about a different type of relation that can hold in the stable stems, which is called being a Mahold invariant. So it's a kind of technical definition. I'm just going to write it and then I'll just give you the idea of why it's useful. So suppose I have some element alpha in the nth stable stem, then the R Mahold invariant of alpha is the coset of completions of the following diagram. So I can start with alpha and represent it by a stable map from a stable n sphere to a stable 0 sphere. And now we've heard about Lin's theorem earlier in the week. So Lin's theorem tells me that this is like the C2 Tate construction on the sphere after 2 completion, which I'm always doing. That Tate construction has a different formula, which appears, for instance, in work of Greenlees and May. So I'll write the symbols here. It's some sort of infinite stunted projective spectrum. And I'll write down what this is in a second. Okay, so what is going on here? So this is actually the original form of Lin's theorem before everyone decided that was the Siegel conjecture. And P infinity K is the Thom spectrum of the K-fold sum of the tautological line bundle over RP infinity. So you should think this is something like RP infinity, where you've got a cell in every dimension up to infinity, but the bottom cell is just in dimension K. But K could also be negative because we're doing spectra. P infinity minus infinity is the limit over K of P infinity minus K. So this is something you should think of as having cells in every positive and every negative dimension. And somehow after 2 completion, that's the same thing as the sphere up to a shift. Okay, great theorem. So this is the definition. Oh, and I have to say one more thing. Where this n is positive, as long as alpha is non-trivial. So n is positive, is the minimal integer such that this left-hand composite is non-trivial. So left-hand composite means go into there. And the reason I have a minus n plus 1 sphere appearing and I have a coset of completions of the diagram is if I went one further, I'm assuming that that's a 0 map, and the difference between this and suspension of P infinity minus n plus 1 is exactly this type of sphere. Okay, kind of a technical definition. The only thing that really matters for the purpose of vibes is that it uses RP infinity, which is the classifying space of Z mod 2. Okay. But just to maybe give a feel for what the Mahold invariant does and why it might see something interesting, you can plug in, say, the degree 2 map in the 0th stable stem, and its real Mahold invariant will contain eta, the first hop invariant 1 map. You can plug in eta, and you get nu. You can plug in nu, and you get sigma. And then famously from Piotr's talk like 2 days ago, there's not another hop invariant 1 map, and this is seen by the real Mahold invariant. The real Mahold invariant of sigma doesn't contain some like ostensible next Greek letter. These are the only ones. It contains sigma squared. Okay. So this Mahold invariant is kind of interesting. If you want to actually compute it, you have to study the stable homotopy of these P infinity Ks, as K ranges from like -1 down to minus infinity, like 1 at a time, and see what the differences are. That seems like So it's something that you can sort of compute as long as you can compute stable homotopy groups of projective spaces. Okay, so why is it interesting from the perspective of symmetry? There's the following theorem of Stolz from '88. So let's suppose that I have some very exotic sphere, sigma n, corresponding to an element alpha in the nth stable stem. And suppose I have some other very exotic sphere, sigma n plus capital N, corresponding to some beta in pi n plus n stable. If this Mahold invariant relation holds, so if beta is in the real Mahold invariant of alpha, then there exists a smooth Z mod 2 action on sigma n plus n. Let's see. Yeah, let's just say it like this. With fixed points. The lower dimensional sphere, sigma n. So if I have this sort of Mahold invariant relation holding in the stable stems, or really in the stable homotopy of these stunted projective spectra, then I can deduce the existence of a smooth Z mod 2 action on elements which, I don't know where the Lee theorem went. Lee's theorem didn't apply. Oh, this is why I should wear my glasses. It's too high. Okay.
Top middle.
Top middle. This is really why I should wear my glasses. Okay. Yeah, so the 2 was not prime to the order of these things, because we're in the 2 complete setting. Okay, so it gives you something genuinely new. What was the work with Botvinnik? Oh, 17 minutes. Maybe I'll just say, in terms of a proof, what you do is you look at the definition of the Mahold invariant, which is in terms of homotopy groups of spheres and homotopy groups of Thom spectra. You can rewrite all of those things in terms of Bordism, like certain normal Bordism groups. And some of those will translate into free Z mod 2 Bordism groups. And so the Z mod 2 action is sort of popping out because you were looking at Thom spectra over B Z mod 2. Okay. So what did Botvinnik and I do? Well, first we saw what Ravenel did, which was prove a complex version of Lin's theorem. So if you look at the analog of p infinity minus infinity for the complex numbers, it won't be the minus 2 sphere. But what is true is that the minus 2 sphere is a retract of Cp infinity minus infinity. So this is what Ravenel proves, more or less by adapting Lin's proof using the atom spectral sequence. And adapting Ravenel's proof, we can show that the minus 4 sphere is a retract of Hp infinity minus infinity, the quaternionic projective space. I have to write one more thing. So using these, I can, yep.
Is this too complete, or?
Too complete, yep. Everything's too complete until the next remark. So, using this, Ravenel defines what he calls the complex Mahold invariant. And we define the quaternionic Mahold invariant. Ravenel defined this and basically didn't do anything with it. And I asked him like 5-10 years ago if he remembered this and what he thought about it. And he said he hadn't thought about it since 1985. So, but I think now it's like kind of a fun thing to think about. So using this complex and quaternionic Mohold invariant and sort of checking carefully that Stolz's proof can be adapted to these cases, Botvinnik and I show the following. So same sort of hypotheses as above. If I have some exotic n-sphere corresponding to some element alpha in the nth stable stem, and some n plus capital N sphere corresponding to beta in pi n plus capital N stable, then if beta is in the complex Mohold invariant of alpha, then there exists a smooth circle action on the higher dimensional sphere with fixed points sigma n, and the expected thing is also true for the quaternions. So if beta is in the quaternionic Mohold invariant of alpha, then there exists a smooth three-sphere action on sigma n plus n with fixed points sigma n. Okay. And the reason this shouldn't be so surprising, like the reason these groups are showing up, is because CP infinity is the classifying space for the circle group, and HP infinity is for the three-sphere group. We also prove one thing that I want to mention, because I think it's kind of maybe interesting for some people in the room. The real Mohold invariant, unless you plug in 1, always gives you something in a higher dimension. But the complex and quaternionic Mohold invariants don't have to do that. But when they do, so if beta is not equal to alpha, then beta is in the quaternionic Mohold invariant if and only if beta is in the complex Mohold invariant if and only if beta is in the real Mohold invariant of alpha. So all of these things agree under this assumption that the quaternionic or complex Mohold invariant isn't just like stupid and trivial. So the reason this is kind of interesting to me is because there's a lot of work that's gone into computing real Mohold invariants over the past 30 years or so. And the reason it's really hard, well, one reason it's really hard is because it's like stable homotopy groups. But the other reason is because you're looking at this RP infinity minus infinity, which has cells in every dimension. If you look at the quaternionic thing, you just have cells in every like 4 dimensions. But the dimensions have to like kind of be the same for alpha and beta. And so the quaternionic Mohold invariant should be a more efficient way of computing things than the real Mohold invariant. And we did like some baby computations in our paper, but we were tired, so we didn't do too much. So I think it would be a fun thing for the right person to do. Okay.
Sorry, so here on alpha and beta is the only, what did you say? It's just alpha not equal to beta?
Yeah, if alpha is not equal to beta. So there's a chance that alpha and beta are the same, in which case this just isn't true. Because if alpha and beta are the same, there's no way that this can hold, unless alpha is beta is 1.
So then does this say that you can upgrade the Zemo2 action to an S3 action?
Yep. Yep. So really what the proof of this is geometric. We show that the three-sphere action restricts to an S1 and to a Zemo2 action, and there's some sort of converse to this theorem that says there's a corresponding Mohold invariant relation. Thanks. Other questions?
Does this show that the difference of degrees of alpha and beta must be restricted?
In the case where all these things agree, yes. So,
Could you repeat the question?
oh yeah, does this show that the degrees of alpha and beta must be restricted? And the answer is yes, because again, we only have these cells in like even dimensions or dimensions divisible by 4 in CP infinity and HP infinity. So really, if this sort of relation is to hold, capital N would have to be 4, divisible by 4. Thanks. Other questions? Okay. Let me give one quick example. So you can get several examples, I think, just by reading classical real Moholt invariant computations. But if you just compute the quaternionic thing straight up, you can show that sigma cubed is in the quaternionic Moholt invariant of nu cubed. And this tells you that there exists a smooth three-sphere action on a certain 21-dimensional exotic sphere with fixed points, a certain 9-dimensional exotic sphere. Okay, and you could get all sorts of things. You can also iterate, so you can increase the degree of symmetry by saying something is an iterated Moholt invariant. All of this is in the paper. Okay. The problem with the Earth being like a standard three-sphere is that the clock keeps going.
I was not aware that the Earth was a three-sphere.
Two-sphere. I think I said earlier there was an off by one error. I guess I meant later in the talk. Okay.
Space-time.
Well,
that's not a standard sphere. That's not a standard one.
let me give one remark where now I'm back to odd primes. So if P is odd, then in some old work, Schultz observed that there's some sort of connection between the homotopy of Z mod P lens spectra and smooth Z mod P actions on exotic spheres. And I want to mention that in work in progress with Oliver, we're sort of attacking the same sort of smooth Z mod P actions on exotic spheres from the perspective of genuine Z mod P equivariant homotopy theory. So the study Z mod P actions with genuine Z mod P equivariant homotopy. And for people who are familiar with like the isotropy separation sequence for computing, say, RO Z mod P equivariant stable stems, these sort of things show up naturally when you take that approach. So there should be some connection between what we're doing and what Schultz did. And the sort of proto-theorem is that if we have some element in the RO Z mod P graded stable stems, satisfying some hypotheses, which we need to make sure we know, then there exists a smooth Z mod P action on some exotic sphere of dimension, the dimension of the representation V. Sorry, I should raise this. And we can say what the fixed points are. So something like sigma, sorry, S, V, Z mod P. Does that look about right? Okay, one thumbs up is good. All right, so the upshot of this is that if you have some other way of computing the Z mod P, RO Z mod P graded stable stems, then you also have some way of deducing something about Z mod P symmetries. So you can detect actions using pi fancy star Z mod P of the sphere, and these groups have been studied. For odd primes, there's some work of, oh, okay, I have to spell right, Shimmick, and there's some work that I've heard about of Ho and Zhang. And I'll just say out loud that at the prime 2, there's a lot of work about the RO Z mod 2 graded stable stems. So that's Belmont, Duggar, Guillou, Isaacson. Okay. So there's a lot of work just sort of in this direction already without reference to exotic spheres. Wondering how much more I want to tell you. Okay. Well, let me tell you in the middle board something. I wanted to write this on the board, but maybe it's better to not do it. So the Mohold invariant is conjectured to do some sort of redshift. So the empirical evidence suggests if you plug in some element, which is Vn periodic, then its Mohold invariant will be Vn torsion. And this result with Botvinnik is saying that the Mohold invariant is also sort of increasing the degree of symmetry. So I think a natural sort of question is if there's some sort of connection between height and degree of symmetry. I won't put it on the board because I have no idea how to answer it, but okay. What can I tell you in 3 minutes? I guess since I put Tillman Bauer's name on the board, I should tell you something about work with Tillman Bauer. So far, none of these actions have been free. We've been saying what the fixed points are. There's actually classical work of Brumfield which studies free circle actions, also free Z mod 2 actions and free 3-sphere actions on exotic spheres. And the basic observation is that if you have a free action of the circle on a 2n plus 1 sphere, then you can take the quotient, and that gives you an exotic CPN. And there's a way to try to classify exotic smooth structures on CPN by looking at the 0th stable co-homotopy of CPN. All right. So again, this sort of study of free actions basically reduces to a problem in stable homotopy theory. And I guess the strategy or the work in progress with Bauer that I'll mention is that, okay, if you try to compute the stable co-homotopy of CPN, you're going to have like a really bad day because this, I mean, once n gets big, you're just looking at like the corresponding 2nth stable stem. So okay, that's not good. So what we want to do is study the TMF-Hurevich map. So this was computed for the sphere at the prime 2 in this work with Behrens and Mohold. And the reason that this is sort of a reasonable thing to try to study is that in previous work, Bauer computed the TMF cohomology of CP infinity. Now, as it stands, that's like not that useful for this problem because I want a finite n and I need to actually understand this map. I mean, it is very useful, but it's not going to do everything. But what's really important is how Bauer did it. So what Bauer did is look at cofiber sequences like so. Let me just write P. I don't have to keep going. So the last one, I have CP8 includes into CP16, includes into CP24, and this gives me some filtration of CP infinity. And you can hit all of this stuff with TMF cohomology and sort of see what happens to elements explicitly in all of these long exact sequences. And also this sort of 16 speed Atiyah-Hirzebruch spectral sequence will collapse at an early stage. And so if you understand how to lift things from the TMF cohomology of the sphere to the stable stems, then you can sort of push through all of these long exact sequences in an appropriate way to try to get things in the stable cohomotopy of CPN. That's the work in progress. Okay, sorry for going over, I'll stop there.
Well, thank you for a very nice talk. Are there any questions or comments?
So for what you're calling the real Mahold invariant, there's a different equivalent definition involving C2 equivariant homotopy theory about like how divisible by A your element is. Is there a similar description for MC and MH?
Yeah, so both of those should be defined the same way using the Euler classes for like the sort of canonical circle action on C or S3 action on H. And that also, I talked with William Valderrama about this about 1.5 years ago. You can also sort of try to start studying, say, SON actions this way by looking at appropriate Euler classes. But then the computations become like impossible and the definitions also become like impossible. Yeah, thanks.
Any others?
So you mentioned this question if n of exotic sphere is bigger than 0.
Mm-hmm.
So I guess this result of yours gives some examples, like how yeah.
How many?
Yeah.
Well, it gives you infinitely many because you know that the, say, complex Mahold invariant of infinitely many things is non-trivial, but you don't know explicitly what it is. That's like a computation. You could also ask how many elements in the stable stems are Mahold invariant. And I think on either this paper with Botvinnik or a previous paper that I wrote with a similar sort of name, if you know something about the size of the stable stems, you can sort of estimate how many elements are, or conjecture at how many elements really are Mahold invariants. It's something, it's not that many.
Okay, well, thank you very much.